In this video, we keep on presenting the basic concepts and notations of theory of languages for our course on theory of computation. The reverse of a word W is a word of the same length and satisfying that its first symbol equals the last symbol of W, its second symbol equals the penultimate symbol of W, and so on. For example, the reverse of this word is this one. It is not difficult to check that the reverse of the concatenation of two words corresponds to the reverse of the second word concatenated with the reverse of the first one. We define the reverse of a language L as the set of words obtained by reversing each of the words in L. For example, the reverse of the set of words over AB starting with A corresponds to the set of words over AB ending with A. It is not difficult to check that the reverse of the concatenation of two languages corresponds to the reverse of the second language concatenated with the reverse of the first one. We define now the notion of morphism. A morphism is a function that transforms words over an alphabet on words over another alphabet. However, it is a particular kind of function since, additionally, satisfies that the application of a morphism to a word commutes with word concatenation. This means that the image of the concatenation of two words under a morphism coincides with the concatenation of the corresponding images. The image of any word, denoted in a general way as A1, A2 to AN, where each AI stands for a symbol, corresponds to the image of A1 concatenated with the image of A2, and so on. Moreover, it is not difficult to prove that the image of the empty word under a morphism is the empty word. Actually, in order to define a morphism, it suffices to define the image of every symbol of the alphabet, since the image of any word can be computed in terms of its symbols. Let's see an example. We define the following morphism sigma between the words of these two alphabets. It suffices to define the images of ABC, for example, in this way. As a consequence of this definition and the fact that sigma is a morphism, we can compute the image of any word under sigma. For example, the image of this word is computed by concatenating the images of its symbols in order. Note that, essentially, the morphism transforms A's in zeros, B's in sequences with two ones, and erases C's. For a language L, including the domain of a morphism sigma, the image of L under sigma is defined as the language containing the words that are the image of some word in L. Similarly, for a language L that is a subset of the codomain of sigma, the inverse image or preimage of L is defined as the language containing the set of words whose image under sigma is in L. It is not difficult to check that the application of a morphism on a language commutes with language concatenation. We define now the concept of rewriting rule. A rewriting rule is an ordered pair of words, UV, denoted in this way. We'll say that this is the rule that allows us to transform U in V. For instance, this is the rule that allows us to transform AB in BBA. The application of a rewriting rule on a word consists in finding the occurrence of the right-hand side of the rule and replacing it in the word by the left-hand side of the rule. We denote it in this way, specifying which rule are we using. For example, last rule can be applied in this word and this occurrence of AB, which is the left-hand side of the rule. In the result, we can see how this occurrence of the subword AB has been replaced by BBA, the left-hand side of the rule. If R is a set of rules, we denote like this that W is transformed in W' by the application of one of the rules in R. We denote like this that W is transformed into W' by the application of 0 or more rewriting steps using rules from R. Similarly, we denote like this that W is transformed into W' by applying one or more rewriting steps using rules from R. Finally, we denote like this that W is transformed into W' by applying exactly I rewriting steps using rules from R.